17 and 20. And this is particle kinematics, 17. Okay. So 17, it says a bicycle moves with a constant speed. It doesn't say anything about anyone riding it, but I'm making that inference. Okay, so this bicycle moves at a constant speed of 8.8 meters per second, which is pretty fast. Each wheel has a radius of 0.34 meters. The wheel isn't slipping, so it's rolling without slipping. What's the velocity vector at the top point of the wheel? So I'll call that P for top. The velocity vector of a point at the bottom of the wheel. And what's the acceleration? Okay, so what's the velocity at the top? Velocity at the bottom. And then the acceleration at the top and the bottom. And then the last one is sort of an understanding question. Why can't we just find the velocity at some point and then use the fact that acceleration is d dt of the velocity? All right, well, this is the center. And so we're going to, the center on a good bicycle has the same motion as the, whatever, the, it says that the bicycle's moving at 8.8 meters per second. So that's the velocity of the center of the wheel, okay? That's rigidly fixed to the rest of the bicycle. And so if we're trying to figure out the velocity of the top, we want the velocity of the top relative to the ground. And we can write that as velocity of the top relative to the center plus the velocity of the center relative to the ground. The velocity of the center relative to the ground is what we're given. If I'm using a coordinate system like this, and why not? Then the velocity of the center relative to the ground is positive 8.800. 0 for z, I guess, too. And so to calculate the velocity of the top relative to the ground, we just have to calculate the velocity of the top relative to the center. And in any circular motion, if you're calculating the velocity of some point relative to the center, that's treating the center like it's fixed and then just doing the circular motion calculation. So this is going to be omega cross r. That's just the formula for velocity in circular motion. Okay, well, we know that in rolling without slipping, the velocity of the center is equal to negative omega r 0, 0. Anytime it doesn't make a specific reference to what you're taking a velocity relative to, it's talking about relative to the ground, so we can make this assumption. Okay, so we know that negative omega r is equal to 8.8000. And so negative omega times the radius of the wheel, 0.34 was it, is equal to 8.80. And so omega is equal to what's 8.8 divided by 0.34? 25.88 radians per second. Okay, so our omega vector is 0, 0, negative 25.88 in SI units. And why did I go through all this? Well, seems like sort of a detour, but all we're trying to do is come up with this expression for the velocity of the top relative to the center, and to do that we needed this omega vector. Okay. So I use what we knew about rolling without slipping to find the omega vector. Any questions about that part? That's the angular velocity, that's right. But now we're going to use the angular velocity in the expression for the velocity of the top relative to the center. So that's not the answer yet. Right, not done yet. Okay, so the velocity now of the top relative to the center, not a C. This is the circular motion. So omega is 0, 0, negative 25.88. And we're crossing that with the r vector. And the r vector goes from the center of the circle to the point that we care about. In part A, we care about the top of the wheel. So that r vector is in the positive y direction. So that's 0.340. And you get 8.80 back. Okay, still not done. So the velocity of the top relative to the ground is equal to the velocity of the top relative to the center plus the velocity of the center relative to the ground. And so that's 8.800 plus 8.800, and so 17.6000. And so if the bicycle's going, well, if the bicycle has a speed of v, the top point of the wheel at every instant has a speed in the same direction of 2v. Yes. No, no matter what wheel it is, top is always going twice as fast as the center if it's in rolling without slipping. Okay, so now same thing with the bottom. Do we have to go through the calculation again of omega? No, that represents the whole wheel. So we already have the omega. This is still 0, 0, negative 25.88. The only thing that's going to change is that we have a new value for R. For the bottom of the wheel, you go from the center in the negative y direction. So this is 0, negative 0.340. And then the velocity of, what's the answer going to be? Come on, let's be serious. It's going to be 0 because that was one of the things that we use to come up with all these equations for rolling without slipping. But if you forgot that or whatever, the velocity of the bottom relative to the ground is equal to the velocity of the bottom relative to the center plus the velocity of the center relative to the ground. The velocity of the bottom relative to the center is 0, 0, negative 25.88 crossed with 0, negative 0.340, and you get negative 8.8000. And so the velocity of the bottom relative to the ground is negative 8.8000 plus the velocity of the center relative to the ground. That's given at the start. That's positive 8.8000. And so you get 0. So at any point for a wheel that's rolling with its center speed v, the top is going 2v, just that instantaneous, at that instant, the point at the top is going 2v, and at that instant, the point at the bottom doesn't have any velocity. Okay, so now accelerations. We're assuming that the wheel is going, the bike, both wheels are moving with a constant angular velocity. So at first thought, you might think there's not going to be any acceleration of any of these points. But remember that things in circular motion have two types of acceleration that add up to the total. One is the tangential acceleration, and that one does have to do with whether the speed's changing. But the centripetal acceleration just has to do with the fact that it's a circle, and that's going to be there no matter what. So there is going to be acceleration for both of these points. Okay, so for part C, we want the acceleration of the top. And the acceleration of the top relative to the ground is equal to the acceleration of the top relative to the center plus the acceleration of the center relative to the ground. This bike's moving with a constant velocity, so there's no acceleration of the center relative to the ground. The acceleration of the top relative to the center, that's circular motion. And so that's equal to all ripe watermelons will rock. And this one goes away because there's no angular acceleration. So the acceleration of the top relative to the ground is equal to 0, 0, negative 25.88 crossed with the quantity 0, 0, negative 25.88. Crossed with the r vector, that's from the center of the circle to the top. That's 0.340. This one we've already done. So this comes out to 8.8000. And so the whole thing, let's see, what is um 25.88 times 8.8? Okay, so we get 0, negative 227 point what? It's the y, and y is always the weird one. Remember, you switch the sign of y. So 0.74. Important we get that hundredth of a meter per second, right? And then 0. Okay, so does this make sense physically? Yes, we're talking about the top point of the wheel. The only acceleration is centripetal, and that centripetal acceleration then is down in the negative y direction. So what do you think is going to be the answer for D? So the acceleration of the bottom relative to the ground is equal to the acceleration of the bottom relative to the center plus the acceleration of the center relative to the ground. Again, this is 0. This is circular motion. And this part is going to go away. So again, all we're left with is centripetal acceleration. So what do you think the answer is going to be here at the bottom of the wheel? It's just going to be positive because a vector from the bottom to the center is just in the positive y direction. And so this is just going to be 0, 227.740. I remember when I first started seeing like how much you could do with relative motion, like in dynamics, I thought it looked so cool to just comfortably, go from, and it is. It's so fun. you should come join me here. Okay, and then the last question, E, is why can't you just, so like A and B, we calculated the, for example, we calculated that the velocity of the top relative to the ground was equal to 17.6000. Um, so why can't we just say that the acceleration of the top relative to the ground is equal to the time derivative of that velocity, and then that would say that it's equal to 0, 0. Another way was the way to do it. This doesn't work. So what's the misunderstanding there? This is sort of an important thing because this is sort of how almost every problem that we deal with is going to be. The answer is so always be sure that you know whether you have an instantaneous value or a function of time. If we had an expression for the velocity of that point that's currently at the top, if we had an expression for that as a function of time, then we could do it this way. But all we have is just a single snapshot of what it's doing at that instant. And, you can't differentiate that. That's like saying, say that you have, say that you have a function like that, okay? Actually, I don't want to think about it that much. I want to think about it this much. So say that this is a graph of a particle's velocity versus time. Okay? If you have an expression for the velocity as a function of time, you can take its derivative and get the acceleration, right? Its acceleration is its slope anywhere here. But if you just pick a single value off this graph, you can't take the derivative of that and expect that it gives you the acceleration. Like this point right here, the velocity, that's a negative time. This point over here, the velocity is equal to 0, right? So what I'm asking if you can do in part E of this problem is the equivalent of saying velocity here is 0. Therefore, take the time derivative of that, and the acceleration must be 0 too. You can only use the derivative thing if you have it expressed as a function of time. Okay. And then number 20. So a bike with a wheel diameter of 0.72 meters. So I'm just going to draw the wheel. We know that the radius is half of that, so 0.36 meters. And it's moving with a constant speed of 8 meters per second. and it stops over a distance of 10 meters. Um, and we want to know what's the angular acceleration. So let's first, I'm just going to use like the constant acceleration equations that you used in physics 1 to figure out what the linear acceleration of the center of the wheel is. So 2a times the quantity p minus p0 equals v squared minus v0 squared. Remember that one. So 2a times our final position is 10. If we start at an initial position of 0, the final velocity is 0. The initial is 8. And so 20a is equal to negative 64. 32. So a is negative 3.2 meters per second squared. And now we can use what we know about rolling without slipping. The acceleration of the center is equal to negative angular acceleration times the radius, 0, 0. And so that's negative 0.36 alpha, 0, 0, is equal to the acceleration that we just calculated. So that's negative 3.200. And so alpha is equal to 3.2 divided by 0.36. That's 8 ninths, 8.9, 8.8 repeating. I think it's that. Radians per second squared. We want it as a vector. Is that what that you get it? Is that 8 ninths? And so the angular acceleration vector is 0, 0, 8.8 repeating in radians per second squared. Now we have to think, I mean, you don't have to do this, but it's a good idea to go back and think about whether the sign makes sense that we got. All right, so this is moving this way. So what direction is its angular velocity? What kind of component do we have? It's going to be parallel to z because this is in the xy plane. It's going to be, the rotation is like this if the center is moving that way, so it has to be in the negative z direction. So that's the angular velocity. Is this thing speeding up or slowing down? Slowing down, so the angular acceleration has to be opposite of the angular velocity. So it has to be a positive z component. So the sign makes sense. Any questions about that one? Was there one, Max, you were interested in seeing? Okay, good.
I just used the like one of the four schematic thetas and
I don't remember that one. I don't think I teach that one.
like the displacements are now in theta.
Oh, yeah. So you use something like um, 2 alpha times something like this. Okay, yeah, you could use that too. But then you just have to figure out how many radians the wheel goes through to make it 10 meters, right? Did you have to do that? Okay, I want to say one more thing that's relevant to rolling without slipping. So rolling without slipping. So if you have an object rolling down an incline, that's supposed to be round. If you use a coordinate system that's tilted with the incline, then in this coordinate system, um, the velocity of the center is negative omega r 0, 0, and the acceleration of the center is equal to negative alpha r 0, 0. But what if you don't want to use a tipped coordinate system? You want to use a regular coordinate system. So what if you want this coordinate system? Um, well, the solution to that is rotation matrices. And we're not going to use this a lot in this class, but actually dynamics is where this is the most important thing. We're not going to use it a lot. I'll try to point out where it would be used, like in practice. But rotation matrices, and the idea is if you know a vector, I'm going to call it u relative to the old coordinate system, and you want that same vector expressed in a new coordinate system, u in the new coordinate system is equal to the matrix Q times that vector in the old coordinate system, where Q is the rotation matrix that goes from old to new. Okay, so there are three cases that we're going to deal with. If you rotate the old coordinate system an angle of theta about the x-axis to get the new coordinate system. Then this rotation matrix is going across the rows. It's a 3 by 3 matrix. 1, 0, 0. 0 cosine theta, sine theta. 0 negative sine theta, cosine theta. If you rotate the old coordinate system an angle theta about the z-axis, sorry, I'm getting ahead of myself, about the y-axis to get the new coordinate system. Then this rotation matrix Q is cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. And then last, if you rotate the old coordinate system theta about the z-axis to get the new coordinate system. Then the rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. There's almost a perfect pattern here, except the Y version of it throws the pattern off a little because it always does. There's always negatives thrown in with the Y. But in all of these, the axis that you're rotating about, in this case the x-axis, in this case the y-axis, has a 1 in the diagonal spot and zeros in the row and column. And then you have a cosine, a sine, and a cosine in the other 4 spots. The x and the z match exactly. It's cosine and then cosine and then positive sine, then negative sine, and then cosine. The y is flipped, just like it's flipped in the y component of the cross product, just like y stuff is always flipped. Okay, but let me just show a simple example of how to use this. These are all two-dimensional problems. So in two-dimensional problems, all your rotations are about the z-axis, either positive or negative. Okay, so let's say that this is rolling down this hill. And it has an angular velocity of omega. And let's just do the velocity. It works the same with the acceleration. It works with any vector. We want to calculate the velocity vector in a coordinate system like this. And I'm just going to use a radius r. Oh, and let's say that this angle is theta. So first I'm going to do it. This is going to be my old coordinate system. It's going to be aligned with the incline. And that makes doing this calculation easy. So Um, the velocity vector in the old coordinate system is, so it's negative omega, whatever your omega is, times r. Okay, this is getting a little messy. Let me name this something else. I'm going to call this capital omega. Okay, I'm going to call it, well, r is fine for that. Okay, so the formula for this is lowercase omega times r, negative, and then 0, 0. Our lowercase omega is a negative value of capital omega, so this just comes out to be capital omega r, 0, 0. Okay, so that was easy. That's not the coordinate system we want. So now we have to think about how to go from our old coordinate system to our new coordinate system, the one we want. What kind of rotation does that take? We know it's about z, and we know that the angle is theta. Is that a positive rotation about the z-axis or a negative rotation about z, according to the right-hand rule? Any other guesses? Yes, good. So theta is equal to positive theta. I'm going to change this too. I'm going to call this uppercase theta. Okay, so the angle that I always call theta is the specific angle uppercase theta here, positive. And so the rotation matrix corresponding to that coordinate system transformation is cosine capital theta, sine capital theta, 0, negative sine capital theta, cosine capital theta, 0, 0, 0, 1. And now that we have the rotation matrix, the velocity in the new coordinate system is equal to q times the velocity vector in the old coordinate system, which was capital omega r, 0, 0. And if you've never done matrix multiplication before, just have your calculator or MATLAB do it. It's not hard, but and what you get out of this is capital omega r cosine of uppercase theta negative capital omega r sine capital theta 0. By the way, if you want to try this out, the rotation matrix, I would recommend trying it with, the kind of problems you did in physics 1, where you have objects sliding along inclines, and you used a rotated coordinate system for those, right? You rotated the coordinate system kind of manually, just by thinking about trigonometry and, but think about So you know what the weight vector is in a standard coordinate system. It's just because it's just straight down. That's easy. Think about what rotation matrix you would need to go from the standard coordinate system to the coordinate system aligned with the incline. Apply that rotation matrix to your weight force vector and see if you get the right answer, because you know how to. So now you have two ways to compare it, and you can see if you get this. By the way, Twin Cities engineering people, of everybody in here, you're the ones who should pay the most attention to the rotation matrix, because the examples that we're going to use in dynamics are going to be like instant by instant. And so we can always, whenever we have two coordinate systems, we can always choose them to be aligned. If you're doing it over time, which you tend to do in any practical situation, then at every single instant you need to apply a rotation matrix to make those coordinate systems line back up. You know, so when we do rotating coordinate system things, we're not going to, in this class, we're not going to worry about rotation matrices. But if you ever have to use coordinate systems that are rotating, you'll almost definitely need to use rotation matrices at each instant to do those transformations. Any questions? Yes. Right. That's only for a tensor. The vector, so, and this is just for like the deformed people, but the tensor, you have to do two things. You have to rotate the coordinate system, and then you have to re-express the traction on that new face in the new coordinate system. And that's where the two applications come from. So